So here we have two astronauts. Let's just study it before we read the questions. We've got astronaut X and Y. It looks like they're being held together. The string between them is taut. X has this hammer or whatever it is in its hand. They're looking at each other. That's figure one. Figure two, we're looking at it and the containers have switched from X to Y. So that's just what we observe. So they're connected by the taut cable. Initially at rest with respect to a nearby space station. Okay, that's fine. We don't see the space station, but we can draw that in here like this. So here's our space station. X throws a large container to astronaut Y. That makes sense from our interpretation of the picture. Figure 1 shows the astronauts immediately after the container is thrown. So I think what this means is they're trying to imply and depict that he has just thrown this and it's no longer in contact with his hand. No longer in contact with his hand. Figure 2 shows the astronauts immediately after the container is caught. Notice here how the astronaut is holding it. They're like hugging it. They have it, whereas this one is not quite connected. Which of the following describes the motion of astronaut Y? So we are concerned about Y only. Well, let's think about this. Of course, we have to think about it. Astronaut X is going to throw this. So there's really two objects here. We have our first object of focus is the canister. The second object is not, and it's not obvious, is the astronaut system. The two astronauts are tied together, and the rope is taut. So, for the cart to pick up a velocity in this direction, the X astronaut must move to the left. But in doing so, because the cable's taut, Y has to move to the left. So, in figure 1, what happens to astronaut Y? It must move to the left. Choice 1 is out. Or choice A and choice C are out. So we're now to the left. 50-50. Now what happens when the carton is coming in? Well, the container has momentum in this direction. And it loses that momentum when the astronaut catches it. When the astronaut catches the container, it pushes the astronaut back in this direction. So the astronaut Y ends up moving to the right. And that's why it's choice B. You might also notice that in these two pictures we're showing the same location. There is no net displacement of Y or X relative to the space station or relative to where they were initially. The center of mass of this system that the astronauts have is right here. And the momentum of that center of mass is mv. The velocity is 0, so the momentum it has is 0 of that system. And so afterward, the momentum of that system must also be 0. P equals mv, m0, 0. And then there's no net displacement. The center of mass has no momentum, so afterward it must have no momentum. Of course, it must not have changed location. And this, of course, fits like if you are on a skateboard and you kind of rock back and forth from the front to the back, or you are in a boat on the water and you do the same thing. It's why you cannot displace yourself one direction or the other by, say, jumping to the front of the boat or the back of the boat or anything like that. Conservation of momentum prevents that from occurring.